So we looked at some crystalline solids. Now we're going to look at different atomic solids. We're going to look at the covalent network atomic solids. And the first one we're going to look at is carbon. So elemental carbon exists in several different forms. They're called allotropes. Allotropes are forms, different forms of an element. So graphite is one. Here's a diagram of the graphite structure, and here's pictures of naturally occurring graphite. Graphite is the stuff that's in your pencil lead, by the way. In graphite, the carbon atoms are covalently bonded to each other in flat sheets containing interconnected hexagonal rings. And so here is one sheet of graphite, and we see there's little hexagons. So we have a two-dimensional sheet, and then here's another one and another one. And what holds these together are intermolecular forces. These are atoms. They're covalently bonded together, but there's no polar molecules here, so all we have are dispersion forces. So the forces that hold these layers together are fairly weak, and that's what makes graphite slippery. That's why it works well as a pencil lead, because as you push it across your paper, pieces of the graphite slide off and stay on the paper. It's useful as a lubricant. Sometimes you use graphite to lubricate the lock on the door of your car. You can squirt it in there. It's like this powdery fine dust, and it'll spread around and be slippery without, getting sticky or anything. Graphite is also a good electrical conductor. And what happens here is we have extended pi bonding networks. And so we're talking molecular orbitals here. And so we have these orbitals that are shared over the entire sheet. And so electrons can move in the direction of the plane of this sheet. They're not going to move in this direction, though. Graphite has a density of about 2.2 grams per cubic centimeter. If you take graphite and you squeeze it really, really, really hard, like 50,000 atmospheres hard at a temperature of about 1,600 degrees Celsius, like deep down inside the center of the Earth, you squish it, you can cause the atoms to rearrange and form a more dense structure that we call diamond. The density of diamond is 3.5 grams per cubic centimeter. So here's the structure of diamond. Here, we still have these hexagonal rings, but now instead of discrete layers of them, they are bonded in all three dimensions. And so that gives a diamond a very high strength. The diamond cell, unit cell, is similar to the zinc blende cell. But we have the carbon atoms covalently bonded to 4 other carbon atoms at the corners of the tetrahedral hole. I know that made a whole bunch of sense, right? In the diamond structure, all of these, the zinc and the sulfides, they're all carbon. And instead of being attracted by opposite charges, they're actually covalently bonded. So if this would be a carbon atom, and it's covalently bonded to 4 other carbon atoms. When we talked about bonding, we learned that carbon likes to make 4 bonds, and it likes to do that tetrahedral geometry, and that's what it's doing in the diamond structure. Diamond has a melting point of about 3,800 degrees Celsius, which is really, really high. It's very hard. It's an excellent heat conductor. And so that's why you'll sometimes see diamond-tipped drill bits or other cutting tools, saw blades. The heat conduction is good because it's able to conduct the heat away to other substances without getting as hot as something that cannot conduct heat, and it being so very hard means that it doesn't wear out as fast. And the diamonds used for that, of course, are the little tiny, tiny pieces, not the big, beautiful diamonds that people like to wear on their fingers. Another form of carbon was discovered in the 1980s by aiming a powerful laser at a carbon surface. And that makes me wonder, well, whose idea was it to shoot a laser at carbon? Well, people do stuff, you know. And some of the things that you maybe got in trouble for when you were in elementary school or even in high school, you're like, why the heck are you doing that? Don't mess around. Scientists get to mess around. You go to school and you learn enough about it so that you can mess around and be fairly safe. People do blow themselves up, but it's their own fault. So you try to be fairly safe, but you get to do these things that you're like, what if I do this? And sometimes awesome things happen. So this new form of carbon, this is one called Buckminsterfullerene, and that's kind of a crazy name, isn't it? It was named after a guy named Buckminster Fuller. And this is a molecule of carbon that contains 60 carbon atoms, and they're covalently bonded to each other in the shape similar to a soccer ball. And so what you have in here is 6-membered rings and 5-membered rings. And it's very similar to a geodesic dome. Geodesic dome? Whatever, you know what I mean. So that's Buckminsterfullerene. Buckminster Fuller was a guy who did a lot with these geodesic, I gotta look that up, geodesic? They both sound weird, with those dome things. There's variations of this, just generically called fullerenes, and all those names aren't very fun. So scientists gave them the nickname buckyballs after Buckminster, and they're ball-shaped. So in general, buckyballs can have clusters of 36 to over 100 carbon atoms. So you can have these carbon balls that can be different sizes. They're network covalent atomic solids because they only contain carbon atoms, and the carbon atoms are covalently bonded to each other. So of course you get a new material like this, and then people want to do all kinds of fun things with it. And so we've got some really cool stuff made out of carbon. They have synthesized long carbon structures called nanotubes, which are sheets of interconnected carbon-6 rings. And they look a lot like a roll of chicken wire. So this is a cylinder or tube of this, carbon that's chemically bonded to each other, to the other carbon atoms. So you can make a single-walled nanotube. You can make a multi-walled nanotube, which is like several nanotubes nested inside of each other. These nanotubes are 100 times stronger than steel, but only 1/16 as dense. So you get great strength and a low density. And so these get used in things like golf clubs, graphite golf club. They're not making it out of pencil lead. That wouldn't work very well. They're making it out of nanotubes, carbon nanotubes. Bicycle frames can be made with this substance. Really cool. If you take bundles of nanotubes, you can make very tiny wires because these do conduct electricity. Yeah?
Somewhat similar to carbon fiber?
They are carbon fiber. Yeah, very similar to carbon fibers, yeah. There's lots of different subtle variations. Yeah. This is a graphene nanoribbon. At the very beginning of the chapter, we talked about how graphene was discovered using Scotch tape, right? So if you have a long, narrow piece of it, it's like a ribbon. That's a ribbon of graphene, or you can have a larger sheet of graphene. And this is basically one layer of graphite. This is single atom in depth. So those are cool things. Another important network covalent atomic solid are silicates. And you look at silicates, they are extended arrays of silicon and oxygen. And when I see SiO2, I think molecule, right? Well, it's like a molecule, a silicon and 2 oxygens. But that's just the empirical formula. They are not actual molecules. It is a network covalent atomic solid because we have this lattice that's formed of silicon-oxygen bonds, and they just continue throughout the whole substance. This is by far the most common network covalent atomic solid. It makes up about 90% of the Earth's crust. Sand is mostly silicates. So this is very common in ceramics, cement, and glass. We're going to talk about each of those. The formula unit for silica is SiO2, and depending on what its structure is, it can have different appearances. Quartz is one form of silica. In this array here, which is, I find that difficult to look at and make any sense out of, what we've got here are a series of tetrahedra, where the silicon is in the center and it's covalently bonded to 4 oxygens. And each oxygen is then bonded to 2 silicon atoms.
Why are they SiO2 but not SiO2?
Because overall the ratio is 2 oxygens for every 1 silicon. What you don't see is this goes on, here's another silicon and then another oxygen. So each of the silicons is bonded to 4 oxygens, each oxygen is bonded to 2 silicons. And so it is a ratio of 2 to 1. Not immediately obvious by looking at it. This does look like it would be SiO4. Is this a good Lewis structure though? No, what's wrong with it? The oxygens don't have 8 electrons, right? So what happens is you've got over here a silicon that's bonded to other oxygens. Oh, I gotta do this. Okay, and then those oxygens aren't happy either, so this oxygen is going to bond to another silicon. And that silicon is going to bond to 4 oxygens. And it just keeps going like that.
It doesn't have any parity or?
There are no discrete molecules. So each oxygen is bonded to 2 silicons, and each silicon is bonded to 4 oxygens. Kind of have to stare at it for a while before you can start to see it. This kind of makes your head hurt.